not very high spec, so I kind of just get someone moving it's a machine learning project. Yeah. I think that I'm more like that. It's just kind of more yeah, especially if I kind of do things under the project, to try the technical outcome. In fact, one thing I'm doing is I'm following that deep learning course. Agile Method. Yeah, in fact, I didn't know. Okay, no, I use Python. I'm playing with Torch now. Well, okay. I mean, even though it's smooth by accident, it's always a problem. Yeah. A lot of things don't work, and it took me a while. I have a graphics card to run through that. Okay. I spent a lot of time and I gave up basically. I used a thing called Pilot 2. Not Piano. Pilot 2 is based on Piano. Okay. So there's also a new framework called allows you to expand the execution response. So what's the spot cluster? It's like it's like 10 times faster. These guys? So I started by suppose that you look at the company.
Hi guys! Can I get your attention please? I'm yelling! Can I get your attention please? How many of you it's our first time here? Seriously, Alex? Thank you for coming tonight. My name is Vivian Zhang. Most of you know me, either through my events or taking my class. It's such a pleasure, and we just got new equipment, make it more awesome. And tonight is the big show of our bootcamp students. They achieved top 7% in their 5th week of the bootcamp on Kaggle.com. And several of them have interviewed with the Kaggle #1 Open. I'm really proud of them. So the whole team is ready to present and just give you a little bit of history about us. Some of you might know I started to do volunteer teaching since May 2013. And in November, I started my school. And I offered the part-time program in the past 18 months and graduated 300 students. And this is my very first cohort of full-time program. And we have 6 PhD, 6 master, and 2 bachelor, exceptional bachelor. And they're looking for a job. If you're hiring, talk to us, talk to our grads. They're all awesome. You will love them. Okay, so if you're interested in the bootcamp, there are some flyers you can grab and spread the good word of them. We're doing live streaming. If you want to share with your team, with your friends, feel free. It's gonna on our Twitter account, NYC Data Science, SCI. Okay, so can I pick 2 of you? Tell me, how did you find us? Can I ask you? How did you find this event?
Just meet up.
Meet up?
Mm-hmm.
Did you ever compete in Kaggle?
No.
What's particular thing?
I'm familiar with Kaggle's. No.
Did you know this particular competition?
I might have seen it before, but I don't remember the details.
Okay. Are you in data science position now?
Yes.
Awesome. How about you, gentlemen?
I am a data scientist intern at AXA, and my former manager has designed the Kaggle competition. So
design Kaggle competition?
Yeah.
Design Kaggle competition?
No, I designed this Kaggle competition, the AXA one.
AXA
From
one?
AXA, yeah.
Yeah, for AXA.
Same one.
Wow.
So I was like curious to come here to.
So we can complain to you about how hard this was, right?
So yeah, I was not here when he.
So do you have solution from the #1?
Sorry? I have absolutely no insight about it. It was just my former manager. So.
Unbelievable. We have the competition designer here tonight. Such a pleasure. Thank you. Thank you for giving us the opportunity. Okay, let's get started. From Julian, right? Cool.
Jason, where's the PowerPoint?
Yeah.
I thought it was close.
Yeah.
It's actually not.
Yeah.
Just to introduce you to Julian, he's a very special student. Before he joined the bootcamp, he was a lawyer.
We've been rehabilitating him ever since. It's been a long process, but we won him over to our side.
Yeah, he's on our side now, across the river.
It's been hard not suing people. So thank you everybody for coming. The first thing I'd like to do is introduce a team. And this will be the order of appearance, I guess. Timothy Schmeier, he is in charge of our trip visualizations. And then after that is Sylvie Lardot. She is, sorry, that was poor. She worked on the attributes and extracting information from the XY coordinates, which we'll get into shortly. Alex Adler is our trip matching guru. And Jason Liu is our, he was working on a lot of the machine learning algorithms. So we'll hear from him as well. So that was the team. And let me give you a 1 second preview of my prior life. As Vivian said, I was a lawyer. And so I do not have any experience working on technical projects. And so I wanted to get the flavor of what it's like to work on maybe a software development team. And so I decided in the second week of boot camp to see if anybody wanted to join a Kaggle competition. I didn't look very hard for one. This one was open and there was a $30,000 cash prize, so that was enticing. But turned out to be a great project, and when I pitched it to the class, everybody in the class decided to join. So I was now project manager of a 14-person team, which was a little bit unwieldy. But luckily, thanks to Alex, he pointed me in the direction of some good development strategy, and that's the Agile Method, right? And so the traditional method is the waterfall method, which you can see on the left. And this method has its drawbacks, mainly that you need nearly perfect knowledge of what you're going to encounter throughout the course of your project. And you plan for it and you budget your time for it, and hopefully by the end, you'll do it within the right time frame. Whereas the Agile method focuses on an iterative process in which you create your model early on in the system, and then you constantly iterate over it and keep improving the model. And this was perfect in our situation for the Kaggle competition, where we were able to submit practice submissions and get scores on them and see if we're improving or not. The iterative model, once we had our first rudimentary model in place, and Alex will actually show you when that model was in place, you'll see we keep increasing and getting better and better. So that worked out well for us. I wanted to give you guys a little introduction into the competition. So the AXA Driver Telematics competition asked you to identify a driver's signature based solely on 2 parameters, the XY coordinates of their driving trips. Right? So when you get the data from Kaggle, it comes in the form of a large zip file with about 2,700 directories. In those 2,700 directories, all are basically considered 2,700 drivers of interest, and within those directories are 200 files, 200 CSVs. And those 200 CSVs are trips for each of those drivers, right? And those CSVs consist of 2 columns. There's X coordinates and Y coordinates, and each observation accounts for 1 second in that trip. Right? Now the problem is that your boss inserted an unknown number of false trips into each driver's directory. And the only thing we know is that there are fewer than half are false trips. So it could be anywhere from 1 to less than half of their trips. And so the goal is to use just these XY coordinates to develop basically a fingerprint for each driver to determine for each trip what is the odds that that trip belongs to that driver of interest.
Sorry, just how many trips did you send in to each driver?
200 for each driver.
250,000 total.
Yeah. So, yeah, as project manager, I scheduled weekly meetings. We didn't stick to it all the time, but we tried, and worked out pretty well. Eventually, at the beginning, actually, I split the team. 4 teams a little unwieldy, so I split them into 2 teams. And then as the project wore on, eventually we kind of merged the teams and took the best ideas from both and combined them together. So one of the first tasks I was in charge of was I sent out a script to everybody to read in the data, so that if my thought was if everybody had the data read in from Kaggle onto their machine in the same directory structure, put into binary files so that they're quickly read into R, that will help everybody stay on the same page later on as we progress and write all our own algorithms. Hopefully they'll work on the data the same way. So after I sent that out, then actually it's time for me to pass it on to the next presenter, which is Tim, and Tim's going to talk about how he visualized the trips.
Thank you.
Sorry, can I ask you?
What's up?
Was the purpose to figure out I heard you again, which trips belong to which driver?
The purpose was to figure out the odds of this trip belonging to the driver who's directory there.
The owner,
For some
basically
how
the
they-
owner of the vehicle. So anybody can be in your car, but it's whether or not it's the owner of that car.
So given a new trip, you get a new trip, you'd be able to accurately.
Well, actually, the question is more like whose trip does not belong to the owner of the car.
So for each driver, you want to give each of the 200 trips
Yeah.
an odds.
For each car,
Yeah.
like think about the 2,700 collections of 200 CSVs as a car, and then the 200 CSVs are each trip taken by that car.
Yeah, no, I know. Yeah. But for each trip, you want to give the odds of that actually being a
You
real
want to
trip.
know if it's the owner of the car or not the owner of the car. It's an insurance company.
So don't you know how
How do they collect the data?
Julian?
How did they collect
Collect the
it?
data, yeah.
It's unclear. Well, my thought is they took real driver data from GPS coordinates from the car.
The AXA.
You could help us, but
I think it was with data that with really strong nonlinear transformation.
so could you say that again?
Sorry, I think it was real data, but with very strong nonlinear transformation because they were worried about anonymization.
Mhm.
But how do you get, like if I'm driving, how do you get my data?
I'm just, I don't know the deep.
Yeah, that information wasn't provided.
Okay.
Is the answer to your question?
That's great.
They're not watching right now, as far as we know.
I'm not driving right now.
Right.
Is there held out data for evaluation at the end?
Sorry?
Is there held out data that?
Right. The way Kaggle works is they score you on the full data set, or every time you submit your response, they score you on everything, but they only show you your score on half the data or a third of the data available. So you only know how you did on a portion of the data, and then the final results are actually based on something you couldn't see.
Right.
So that keeps you from just being able to overfit the data to the point of view.
So you were told which trips are.
No,
No, this is all unsupervised.
Unsupervised.
I see.
Yeah.
Yeah. So let me recap, right? All we have is XYs for a driver. We have 200 trips, and we have to determine if it's the driver of interest or if it's somebody else, right? That's all we have. The evaluation, I think in this case, was you get evaluated on 2/3 of the test set, and then they hold back your score on the private part of the test set. And so there's actually 2 leaderboards. There's the public leaderboard, and then there's the private leaderboard. And so, you don't actually know how well you did on the private leaderboard, and that's to make sure that you don't just overfit to the test data. And so, basically, Julian's introduced the project. Hopefully, I've kind of given it a nice summary. And so, my job here was to visualize the trips, and so, we kind of showed something that looked similar to this earlier, which all 200 trips by a single driver, right? And so this is driver 1, if you have the data. And these are all 200 trips. And what is provided in Kaggle is that they will tell you that some of these trips are repeated, and they're either rotated and or reflected around your 360 degrees, and they say that's to provide somehow to protect driver identity or something like that. I'm not really sure, but anyway, that kind of suggests an immediate strategy of just rotating them back, right? Because now, if we rotate them back, if the trips align perfectly, we know that they are the same driver. We don't know if that is the false driver or the true driver, but at least we know it is those 2 trips will map to a single driver. And you can actually see, if you look right here, you can actually see these 2 trips are exactly identical. They're just rotated just a little bit, right? And so what we did here, or rather what I did here to kind of visualize the trips with time, is kind of created an animation. And in the CSV, every XY coordinate corresponds to 1 second in time. And so you can actually track where these cars move over time. And again, here are 2 obvious trips that are pretty much exactly the same, but are rotated just slightly. And so, I'm not going to bore you with the code, but if you decide to rotate those back, and I had Jason's help for this. He had quite a clever way to rotate everything right here across the x-axis. You realize that there's a number of trips that overlap, and they're different just by a slight amount. So, you kind of wonder, well, why is that? Why are they? These are obviously exactly identical. Why are they just a little bit off? And it's not by time, because if it was by time, like let's say they got held up at, 100 stoplights that day, you would just expect that they would be kind of left shifted, right? And so what it is also provided in the Kaggle information is that they can trim off some section of the beginning or the end of the data, right? Some amount, and you're not really sure how much. And that has actually kind of a large. So basically, the script that we wrote will rotate everything down to the x-axis, the final point, right? So the final point, or I should say the farthest point in any trip, is rotated such that it's on the x-axis here. But what you see here is, you look at this trip, and this trip, and this trip, those are all the same trip. Right? They have the same shape. It's pretty obvious. And so why did they not all align? And so kind of one problem with the script is some of these have been reflected around kind of the middle point here. And so if you want to take a look at this trip versus this trip, it's obviously related by a reflection right here, right? And another part is...
It's actually a reflection of the x-axis, right? Not the y-axis.
So this one and this one are reflected along the x-axis, here and here. These 2, green and pink, are reflected about this axis here, right?
Another way to think of this is if you drive in one direction and then take the same trip back, that counts as 2 trips. So your GPS will start at 0, 0 on the way back, and you'll basically just flip that trip on the y-axis.
Right, and so basically, the script that we wrote actually takes a look at the majority of the data points, and it will always flip it up. So if you imagine this as 4-quadrant space, right? We have 1, 2, 3, and 4. It'll flip things based on the majority of the data from quadrant 4 up to quadrant 1. What you see here, it did not do that with the green trip. And why did it not do that? Well, there was some trimming either at the end such that the length of this trip is different than the length of this trip, and so the majority of the data is different. So the majority of the data in this orange trip is on the top, the majority of this data on the green trip is on top, but they don't align, right? And so there's kind of at least some problems we've identified with the script as far as, you know, we can't account for when they trim the beginning or the end off the data, and it doesn't flip it and overlay it exactly right. And then the other thing we didn't do at all, we didn't address this issue at all, is kind of this rotation here. That's very difficult to deal with. And what we decided to do, or rather actually after looking at the majority of the data, we decided that there were so few trips that this applied to that we could just neglect it, right? And so we didn't actually address that. And so kind of as a refresher here, let's move back up. This is kind of what the trips from driver 1 look like before rotation. And then once you rotate and flip everything, this is what the trips look like after the application of our rotation matrix, right? And so not only does that one trip we were able to pick out before align, but now a number of trips that we wouldn't have seen before also align. And so now we can, this is basically a dimension reduction trip matching strategy where now we can say with confidence that a certain number of trips are due to one driver or another driver, right? And so that's kind of the basic idea there. Any questions so far?
What are the units on these axes? Like, what is this plotting?
So they're just XY coordinates. So I think they're just GPS coordinates, but they're not actually mapped to any real world location.
Right, it's meter per second.
Yeah. But we don't know exactly where in the world this is important.
Yeah. People on the forum had decided that it's got to be in meters per second because otherwise the speeds were unnatural. So there were, you know, okay, we're gonna treat each position as, you know, meter change, but again, change in such a way that you could never overlay them on a map and decide, well, this person's going to the grocery store every day, because that might be too easy. Yeah.
Quick question. What do you mean by dimension reduction?
Yeah. So initially you have 200 trips, right, per one driver, but let's say 100 of them match up and overlay, right? So you can basically treat all 100 of those trips as one trip, right? For the for assignment purposes, do they go to driver 1 or unknown driver? And so that's kind of the idea of this dimension reduction. Does that make sense? Touch base with
just to kind of play devil's advocate, like, isn't it possible if, you know, 2 different drivers make the same trip?
Yes.
Devil's advocate. I mean, sure. We can't say with absolute certainty, but given that the trips were imputed, we hope randomly, right? That would preclude trips being driven in any different cities by different people, different starting points.
Sure.
The probability of that is pretty low.
Yeah.
So I think with absolute certainty, no, we can't say
Is it
that.
pretty low?
I'm sorry?
Well, it depends.
Is
You know,
it really low?
mom or dad could go pick up Junior at the school. You know, it's the same route but just a different driver. So it really.
I don't know. No, you've got cities that are built on grids, and people go from, you know, West 4th Street to West 10th Street in, you know,
The geography of
50
Manhattan,
cities.
for example, you're bringing up is much different than any other city. I mean, nobody's going to go from Queens to Brooklyn the same way that they're going to drive in any other city because they're constrained by the natural topography, right? So,
but in any city that has a grid. to play devil's advocate a bit more, I don't know if the probability is necessarily that low.
But if you look at any city, there's not an exact grid. I mean, any city has some, like if you take Boston, for example, they're not like built on a grid at all. Like it is confusing as hell to drive in Boston because they've got circular streets, they've got streets that don't exist on a grid.
You've just picked a city that isn't built on a grid.
But there are many examples of that. And every city has its own quirks.
Absolutely.
Yeah. So
It doesn't matter, it's like, it's only one.
but to get around devil's advocate, you know, hopefully the attributes we build in next will help distinguish us between those two drivers if they do happen to somehow take exactly the same number of left and right turns in sequence.
That's probably a very quick answer, but in the way that Kaggle cut off some of the endpoints of this data, did you find that to be random, or did you do any searches to?
To be honest, we didn't look at it too much. Yeah. Or at least I didn't. I don't know if anyone else did.
So for which trip do you decide, you know, to do the rotation and the reflection? Because you have 200 trips, so I mean,
we rotate all of them.
all of them.
All of them.
Yeah, eventually, as I'll get to in my part,
So
the rotation scheme that I used was to bring the final point down to the x-axis. So for every trip, you basically end up lying it all along the x-axis, as long as that final point exists there. If the trip was out and back during one trip, then it will take that last point and bring it down to the x-axis. If it was a long one-way trip, it'll bring that point down to the x-axis. So everything just ends up being on the x-axis, hopefully in the first quadrant manually, as I'll get to later on.
Yeah, so if you notice, every endpoint ends up here. So we rotate all of them.
Okay.
All right, so you rotate and normalize. Because okay, we've got it.
Yeah, there'd be a little more detail, and then fill me with those questions because I'd love to answer. And then
Jason, this is Jason, everyone. Say hi to Jason, and he's going to take the next part.
Okay. I think it's actually Sylvie. Yeah.
So he's going to just intro the.
Oh, right.
Oh, he is?
Round of applause for Prezi, everybody. Prezi. Keeping data science presentations interesting because it's not IO slides.
Excuse me. Before start the presentation, I would like to share some of my thoughts. And thanks Julian and team give the basic introduction and general picture of the competition. And a little background about my personal taste on this competition is this is a competition started from an insurance company. And then why the interest about the telemetrics is because different people have different driving behaviors. So we prefer to know whether we can really distinguish different drivers by their driving behaviors. It's like they drive fast, they typically drive slow, they typically turn sharply, or they turn slowly. So my personal taste is that I don't want to do trip matching, but unfortunately trip matching is one of the most successful way to get the final score high enough to enter the top 10 level. So we'll try here. So after the basic background, I would like to tell about the general machine learning strategy and how we actually conquer this problem. And the first thing first is that we have relatively ambitious goal is like we want to reach the top 10. And then the first thing is we need to know that for the data science, there's famous phrase called garbage in, garbage out. So we need to really think about what's the important thing we care about, what kind of attribute is important to understand the which driver, what the behavior of the drivers. So start from there, we basically create a large chart to say what we care about. It's like positions, radius, how far it drives, which direction, times. Yeah, sorry.
This is mimicking the trips of drivers 1 through 100.
Yes, so relatively we created a fairly large table. And then if you're interested, we can share it later. But now, first thing, we will give the presentation to Selvi, and she will talk about her feature calculation.
Okay, cool. So I actually did the boring part, feature engineering, so it's really not going to be sexy. I'm trying to be fast. So you have this XY position on the first part of the creating features, like what can I extract from this XY position? And what you can do is like get the distance, you can get the velocity, speed, acceleration, jerk, on like angle change. And like that, you have a bunch of distance. You can also add some Boolean. Like for example, in this trip, sometimes you lose point. Like you add some x equal 100 at some point, and then suddenly you have x equal 300. That's like 1 second after. So you're like, okay, probably either they lose GPS or they went in a tunnel under a bridge, something happened. But you can't calculate anything with that. You can't have an average. If you keep that point, your average speed is going to be really bad. So it's a simple way of dealing with it, but I just put a Boolean. I was like, okay, like that we can remove this data point and calculate an average speed. And it's going to make sense. And then I actually turned my trip to, like at the beginning, oh, I think there's something about it. No, okay. I decide my trip is going to go north and right. And I put all my car like that I can calculate the number of turns. Like, I can calculate the number of turns to the right, calculate the number of turns to the left, or like, maybe it's useful later, who knows. So when you have all this data, then you can do a summary of your data, because your goal is to have one line of feature for your whole trip. And to do so, we have like length of trip, total distance driven, so distance from start to end, which allows you to calculate the path efficiency, like how many turns do I have is actually included in that. We took the mean, standard deviation, quantile, velocity, speed, acceleration, jerk, and angle, and the total number of turns. And from that, we can also have the angle from start to end, the total angle change during the trip, and the absolute change, which gives you the turn efficiency. And that gives you a bunch of features that it may be too many features. That may be a point, but like I tried them using GLM with a lasso to select some feature, and I actually had a good score. So I thought it was good number of features to give to Jason to continue his modelization.
And beyond those overall features, I'm also interested about the so-called event-driven features. It's like, let's say the car stopped, and after 5 seconds, what's the average speed of that car? And let's say the car going to stop, what's the average speed 5 seconds or 10 seconds before that stop? So I also kind of create a uniform function called find events, and then I can mark all those event points, and then I can calculate the average property of that event, what the average speed, what the average acceleration, or what the standard deviation of those acceleration, what's the standard deviation of those speeds. And in the next, I will turn to Alex about his trip matching.
So first of all, quick pause. Any questions so far? We've covered a lot of stuff, covered a lot of ground, or maybe not enough ground, depending on how we do it. Yes?
Quick question. You were selecting with NASA. I was just wondering your thoughts on what you think about variable selection using lasso.
I'm not working with lasso, and that's
I did that. I wanted to check whether my feature section made sense, and I couldn't run the GLM. I had too many features, and it was really way too also. So that's why I did a lasso. I didn't work well. I actually had a good score with them. Not enough, but it was pretty good. So, yeah.
There's a lot of literature out there saying, variable selection with lasso is not the most appropriate, but I was just wondering, you guys are PhDs, so.
Yeah. No, it was more like I just wanted to check if what I was doing was making sense.
So how many features do you generate?
I had 56 features after that, which by itself is not that many, but because we have so many drivers, we're like fitting a GLM for every one of them. So it was slightly slow.
Did you try any other?
Like a lot of these features are correlated. So because I took all the quantile, like speed, acceleration, jerk, so of course they're all correlated. So it doesn't really make any sense to just run a GLM. You want to like remove some of them. So lasso is a quick way to do it.
When you had your GLM there, what was your Y variable?
We will talk about the machine learning parts later. Here, still we are focusing on the feature generation.
Still on feature space. Yes. Excellent. So, my name's Alex. I'll be talking about this idea that similar trips equals similar drivers. And this kind of came out early on in the competition, but I think was later verified by a forum post that I do not have the link for. But essentially somebody in the insurance space said that, well, the way we actually do it in the real world to decide whether the driver was the owner of the car or not is to just see where they were going. They have the personalized, the very personalized data. They weren't dealing with these same sort of rotated and transformed sets of trips. So a few people on the forums were experimenting with ways to kind of undo the magic that AXA so kindly kind of waved their wand and randomized the trips for us. So my goal was to try to decide from these XY coordinates which trips might be similar. So as Tim mentioned before, and I'll summarize again, our raw data looks like this, and every trip that starts at 0, 0, and ends at some XY point at the end of the trip, when maybe the driver turns off the car or whatever it might be. And then of course we have trimming that might take place. And then we've already talked about how we might rotate these trips. In my case, for example, I'm not only rotating the final point is on the x-axis, the positive x-axis, but I'm also flipping the trips so that most of the coordinate points end up in the first quadrant, and that means I'm doing an x-axis flip, but also a y-axis flip. So if most of the points were on the negative y side, I flip it into the first quadrant. If the points were on the negative x side, I flip them into the first quadrant. So the goal is to sort of get everything mostly in the first quadrant. And as we can see at this rudimentary stage, as Tim mentioned, we can start to see some similar features. For instance, here, again, these trips are perhaps trimmed, but this is clearly not enough for us to visually inspect and say these two trips are the same, or even know which trips they are. So the approach was to compare these trips, compare the Euclidean distance, which is the distance measured between each point on the path, now that we've rotated them, and see which ones are similar. So once we've flipped and rotated them, obviously we don't want to calculate all 20,000 trips per driver. That's a lot of calculation. So Jason actually came up with this great idea to rough pass filter, which is we're not going to consider trips that are very, very different in their size. There's no way that these two trips are the same trip. Agree? Everybody agree? Great. So what I basically did first was say, okay, what's the range of x's and the range of y's for each trip, and make sure they fall within about 20%, because as Tim mentioned, we are trimming some of the fat at the beginning or the end of the trip. So, for example, trip 2 and 5 here would not be compared in the following algorithm. So we immediately check the if statement on this, and this shaved down, I think, our computation time by about 30%. Big savings. So instead of calculating 20,000 trips, we were only calculating about 1,000. Nice work there. So once we've determined which trips to compare, the Euclidean distance for each trip was taken and normalized based on the maximum y distance. So now that we've rotated everything, basically the points are pseudo one-dimensional in that all the points end on the x-axis, so that we're basically just dealing with y values. And so I normalize by the maximum y value. Larger trips are naturally going to have larger Euclidean distances with respect to one another, even if they are similar. So this is a way to say that larger trips are similar and smaller trips are similar, and be able to rank them by some sort of Euclidean distance feature. So here I show just 10 trips. 10 trips. And these are the Euclidean distances that I calculated. So you can visually see a very pleasing plot, especially considering the spaghetti from the previous slide. This is a lot more organized. I'm not OCD, but if I was, I would love this. And so we can start to see visually, okay, well, trip 76 and 182. So 76, 182 are very similar looking trips. And this is only the top 10 matches that we had. But the question is, exactly what do these clusters look like? And so just as a way to inspect each driver, we're basically dealing with a social network analysis where we have an undirected case of trip 1 matches trip 2, but trip 2 matches trip 3, so trip 1, 2, and 3 are going to be in the same cluster. This is an example of, for instance, what driver 1 and driver 10 might look like for the number of similar trips calculated. And as Tim mentioned, as we said before, just because you take a similar trip does not mean you are the owner of the car. It means that you might be borrowing a car to go to the same place, these sorts of things. So our first thought as far as a feature was, well, any trip that's a duplicate, we're just going to say that was the owner of the car. Didn't really work out that way. As Jason's going to talk about a little more, there's a lot of back and forth as far as how to actually turn this trip matching into a feature that would aid our model. And we eventually did get there. But what I wanted to show here was just exactly how many duplicate trips we're talking about and exactly how many clusters of those duplicate trips we're dealing with for just an example of these two drivers. So at the end of the day, what I ended up doing was, rather than saying these are all in cluster 1 for driver 10, cluster 2 for driver 10, cluster 3, and ascribing some sort of probability of car ownership, what we say, okay, well we've got a distance measure that's very liberal. So these are roughly the distance apart on Euclidean distance. And then we're going to narrow that distance. And now some trips that are not very close together get singled out. And so we, at each of these stages, as we go narrower and narrower to only the closest matches, we add a score so that we get some sort of trip similarity for these trips. And that was eventually the solution that Jason found worked well with our GBM. So that's the part I have for now. Any questions on the trip matching feature? Yes?
Yeah, this seems really cool. I'm wondering, so you use the Euclidean, the distance to cluster. Mm-hmm. What type of threshold do you use to separate the...
That's a very good question. So what I show here is, and the numbers I'm going to spout are kind of arbitrary because again we're doing, there was quite a range. We found that through a few of these visual inspections, which were monotonous but also very gratifying, we found that maybe a threshold of 2, for example, was pretty good and covered about 50 to 60 duplicate trips. But then going out to, say, 5, then we start to get some false positives, some false matches where one trip did not actually match the other one by visual inspection. What we did for this sort of matching, and actually I show here in the green, these links between this trip and this trip, for example, this green link means that they were a very close match. The gray links are not so close matches. And so when we were thinking about clusters, the idea was we're gonna throw away the chance that we might miss some false positives out at the far distances, but we're going to focus in on these very narrow points. And then ultimately that led to the idea of doing this sort of stepped threshold. So there was no one threshold to rule them all. It was sort of a conservative estimate to say a very narrow threshold. But generally, the duplicate drivers were at, I would say, about a fifth to a sixth of the maximum that were actually sampled by that first pass that I showed you, the 20% footprint of the trip. Any other questions on trip matching? Yes?
So how do you use Euclidean distance to calculate the Euclidean distance?
R has a very fancy function called dist. The default is Euclidean. The important, that's actually a great question I didn't talk about. When we look at these comparisons, you can't take the Euclidean distance for two vectors of different lengths by default. So when we were looking on the forums, what some people were doing, say you wanted to test these two, even though in this case we're not, they would repeat the smaller trip, loop back over the first part, so start at 0 every point, and then we basically just repeat that trip and calculate the Euclidean distance there. That's a little bit weird because we're imputing values that do not exist. Tim actually came up with a really good idea, which was instead of imputing, it takes up a lot of computational time and also adds these sort of errors that we might not want. We're just going to truncate the longer trip. So that was done, and actually all of this is freely available on our RPub, so if you want to look at any of our code, feel free to hop up on there. I think we can get a link by the end. But the short answer is we made the vectors the same length by just taking the shorter trip and truncating the longer one to be matching that shorter trip.
Okay, so basically my question is, if one person might take two identical trips, but I mean for each corresponding point within that trip, they might not match because they might stop by the traffic, and the sample point maybe will not be identical.
It's one of those things that conveniently, at least by inspection, seems to have worked out. Although that does bring up another point. There were trips that matched, and you can actually, when you look at these, and I looked at a lot of them, when you look at them, they would, for instance, be most of this trip. However, maybe here you decided, oh, there was a detour, there was a tree in the road, I have to turn around. So you get a pretty good match on the Euclidean distance, but at the very end there was a change, or that might have been because there was a truncation. So yes, there were subtleties that sort of mess with our ideal match. But then again, we are dealing with trips that have been trimmed on either side, so we can't say, at least with this method, that we've got a 100% match and this is the exact trip. There were some other methods on the forums mentioned. I think what was the method we first looked at?
GTW.
Yes. So there are many ways to kind of compare these similarities. This one for us was the best balance of efficiency. We were able to do this in fewer than 1 day, or less than 1 day of computation, which sounds like a long time, but from what we saw in the forums, they were like days and days of computation. So it was a good balance of computational time and efficiency.
Yes. So another context on this is that even those trips, there is some delay in the same trip, but typically their different Euclidean distance is much smaller than totally different trips. So if you just choose a correct threshold, you can separate those two samples quite well.
Okay. Yeah, if you're sitting at a stop sign, you're on your cell phone, longer than you were the last time you took this route, it's not going to be as different as if you decided, oh, I need milk and I need to go to the supermarket. So these sorts of things kind of work themselves out. Yes?
Is time dimension helpful at all? Have you thought about that?
I mean, it's kind of baked in because each point is 1 second of time. So again, we're going back to the fact that we have two columns, X and Y, and the only information we're given is that the distance is 1 second. Yeah, so it's baked in. But yeah, very good question. Time would play a difference if we had another role.
Yes, and also we need additional computational time to process all those timing information.
Yeah. So this the goal here was efficiency. Are the trips the same? Are they not the same? And some cool social network graphs, which everybody loves. So, any other questions before I pass this off to Jason? All right, Jason, go ahead.
Okay, now it's the interesting part about machine learning. As previously mentioned, that we don't have actually the labels of each trip. Is this belongs to the driver or not? So originally this is unsupervised learning. And for unsupervised learning, we are thinking about the clustering, because naturally we have a bunch of attributes, a bunch of features from each driver, each trip. And naturally, the same driver should have those attributes, features, close clustering together. And we try to think about anomaly detection, and this requires just minimum effort, but unfortunately that doesn't work well, because unsupervised learning means that I actually lose the information, additional information, if we have labels there. Because labels can give us really strong information saying this cluster belongs to the driver or not. So we started to think about the supervised learning, and then actually the information is there. Originally, I think AI insurance companies, they have the information, but they hide those information from us. So we need to find it out. And actually it's relatively easy, because we know that most of the trips in driver 1 belongs to driver 1. And most trips of driver 2 belongs to driver 2. So basically, we label all the 200 trips from driver 1, saying that, okay, those are all from driver 1. And the second, for the next 200 trips from driver 2, we say those are all from driver 2, in order to train our model. This indeed introduced some contamination, but after a while, I will talk about how we avoid those contaminations. And then this also gives us some tuning effort that we can change the parameters, improve the model gradually.
And is it that Sylvie used for the GLM, the cluster
Yeah,
regression?
yeah,
That was the
exactly. I
y-axis,
took 5 random drivers,
Yeah.
and I put them as like negative driver, if you will, and I compare to my driver I'm looking at to build the model, and like also random driver, like 0, my driver is 1, and then after the model, some of the 1 changed to 0, and that's how it's like a pseudo like supervised model.
Yeah. Right. Thank you.
Is this clear? Okay. So one natural start is using KN. The KN stands for the K nearest neighborhood. So in the high-dimensional feature space, we pick one path. We are asking what the neighborhood's path belongs to. Are those all belong to the same driver? Then we say, okay, this tree is from the same driver. It's simply small. We just need to tune the K. But actually, this doesn't work well neither, because basically the relations between different features, they have different distance in the feature space. So some are important, some are not important. We really need to have a hard time to figure out which features are those important features, and we should give a really high rates. And then it turns to GBM. GBM is relatively, I think, is killer in machine learning, is that if you don't care about what mechanics behind it, what's the reason to drive those features, are important to give the prediction. Generally, GBM is a general boost in regression models. This actually combines 2 parts. One is called ADA boost. And the idea there is we have a bunch of weak learners, weak decision trees. So each one maybe just takes several features and make a really weak prediction. Just like the KNN, we have a really weak prediction, maybe just slightly better than the random guess. But ADA boost is saying that if we have really bunch of different learners, we combine the result together, let them vote for the best solution. And actually it works well, but the time is quite, efficiency is really low. So GBM is combining with the gradient boosting machines to speed up the process and get a faster conversion rate. So now we have the machine learning model, we have the pipeline, we have all the features from and also me. And in addition, we also send who's a student here. He basically carry out quality assurance, make sure our code are correct, our feature calculation are correct. Basically, this gives us a relatively good result. It's like Salvi previously mentioned, we reached about the score like 0.7, 0.8-ish, but it's still far from the top. So what's next? Then the next is we think about another approach. It's called iterative process. So originally, this is the original part of our machine learning part. We have the trips from driver A and trips from driver B, and then we put into GBM saying that okay, those are from driver A, those are from the driver B, and probably more driver C, driver D, and then we put it into GBM, make a model, and then get the data feeding back and use the model to predict, saying that are those belong to driver A or are those belong to actually this one belong to other drivers, and then we can kind of sort of have a classifier to identify which trips are truly from the driver A and which trips are free from other drivers. And this result is, I previously mentioned, is like similar to Lasso's method of GLM. We got like 0.7, 0.8-ish score. And then the next steps is we kind of start an iterative process. So saying that, okay, we know those 2 trips are probably from driver A, and those 4 trips are probably, this trip definitely may not from driver A, and then for the next loop, we didn't put those in, saying that, okay, this trip is truly belong to driver A, and then we use the new data to give into the GBM to train a new model. And we use the new model to make new predictions, and then we go back again.
Quick question
Yes.
about the setup. So the wrong drivers, are they guaranteed to be one of the other drivers, or are they just some other drivers, anonymous drivers?
We don't know.
We don't know.
Yes, but typically from driver B, probably those are really from, most of them are from driver B. But this is just illustration. In reality, we basically randomly choose from the whole pool of other drivers. We just randomly choose, let's say, here we have 200 paths, and then we randomly draw 1,000 paths from the other pool, and then to train model. And for the next loop, we say, okay, there are 5 paths from driver A, may not belong to driver A, and then we basically remove those 5 paths away, and then use the rest to fit the model, to train the model. And then use the model to go back and feed data again. So this iterative process keep pushing us forward and forward, and at the end we reach about 0.9. The score reached to 0.9.
So
Yes.
Did you train a model for each individual driver, or?
Yes. I'm going to say that in the next one. It's called machine slave. So indeed, working with a single core computer takes us basically 1 day to finish 1 loop from the data, do GBM, and fit the model. And that's just time consuming because we know from Kaggle every day we have 5 chances to submit our result and get new result to see how it works. So why not use all 5 chances? So the next step we are thinking about is using parallelization, and then we basically use the parallelization package on R, and we use 4 cores, and then it typically takes 6 hours per run to get a new result, and we can keep submitting more submissions every day. And maybe you want to ask why 4 cores here. The main reason is that we are kind of limited by the memory, because each core uses up basically 4 gigabytes of memory, and we soon use up all memory on the chip. And so here is a milestone. We basically change the question from a classroom question to a classification question. And we add more and more features. And we use GBM method to train our model, and we use iterative process to keep improving our result. And also at the end, we add the Alex's trick matching to keep boosting our result. Yes, and then the final one is the.
I just have a quick question. I really like the iterative process. Do you stop when it converges in some sense, or do you stop after X iterations?
Because each iteration is pretty long. Basically, after each iteration, we got the result, we submit once, and we run the next one with 6 hours, and we submit another one.
Yeah, right.
But it will keep improving. And the story at the end is we are still keep improving our result on the training, the published score, lead board, and at the end, our score is actually still. We didn't get worse in the private scoreboard, which means when we use the full data set, we didn't get overfitting in our training data set.
Another question. So did you use your result from Kaggle to tune your model? The number, because it's a common practice for people to use that for averaging or something.
No, the result from Kaggle is just one number. It's
okay.
Just like you basically accuracy. Let's say accuracy is 90%.
But some people might use that number for some kind of ensemble averaging.
They could. I mean, I've read as far as the interviewing the winners, where they take their best and their worst actually, and because you can submit 2 final submissions, and so your last bid is maybe the whatever one to choose. And usually you'd want to choose, if you're novices like us, the best 2 that you have. But a lot of people will hedge their bets and say, well, this one might overfit, but this one might underfit, and that's your score. But as far as including that as a feature, we never got that advanced. This was our first Kaggle run for many of us, for actually all of us. So we didn't want to get too fancy. Maybe in future
That's
runs,
all gaming the system. I mean, but
yeah,
I have this
and that's
to it.
it's a competition, so I mean
Yeah.
that's important, right?
Yeah.
If you're competitive, that's how you need to work.
Just a quick point of information. Were you tuning each of these iterations? Were you tuning within the model? And you mentioned that, but I was just thinking, just the regular way that you tune a GBM or anything different?
Let's say from here, we basically keep the model consistent with kind of the same parameters. But we indeed explore different combinations, like let's say different numbers of different threshold, different numbers of training samples, and then we can compare different results.
So were you using a validation set?
We don't have validation set.
So you didn't create a validation set out of the training data to tune
Yes,
separately?
because basically we have no concrete results in that all those passes are belonging to this right. Actually, if we have those information, it would be nice. We can have some insights in that which features is really important. Here we can quickly tell, okay, these features is really important, but it's still not determined.
Because with GBM, you can take the validation, there's a separate validation set within your training data and tune your GBM parameters on that. Figure out the number of iterations. I mean, that what you described over there is actually part of that model. So I was just wondering whether you had that as part of it.
No, because this here is more like we are changing the input. We change the input.
Yeah, that's right.
Yes. Yes, also another thing is that GBM is a little bit sensitive to those outliers, so we don't want to get really like overfit to those outlier data samples.
Well, I mean, you're iterating so many times, you're sort of learning from the last week learner that hopefully if you use magnets, for example, you won't pick them up.
Yes.
Right? Yes. So if you use that, then you'll take some percentage of the data and build that, and hopefully you don't have the outliers there all the time. That's one way you can.
Yes, that's suggestion.
The best part about all of this is that you can still make submissions in this competition even though they're not eligible for the $30,000 prizes. So if you like what you saw, you can build up on ours or scrap parts and add all you want.
I'm really interested in the code of how you guys did the feature selection.
The thing is like you have to remember it's like an unsupervised learning. We made it be a supervised learning, but at the idea of it is like unsupervised. So it's kind of hard to turn your GBM. That's what, because for each driver you only have 200 trips. And you can have fake driver to be like your control, but you still have not a lot of data per driver. So you can't really do a cross-validation on 200 points. I mean, you can, but it's not going to give you good results specifically because you remove part of the
challenge is you're getting a signal from a lot of data underneath. So it's two levels.
Yeah.
That's all the time.
Another comment is this is the whole competition is carried out during our classes here. So the good thing is that each run takes like a couple of hours, so we can still focus on the class. But the bad thing is that we don't have enough time to really tune the parameters, see how it works. But luckily we keep improving.
This is a part-time job.
So at the end, this is the nice visualization made by Alex.
Oh yeah, so this is the score of the entire leaderboard as a function of time, and the rank is on the x-axis. So this is the ROC curve, so we're normalized between 0 and 1. But they said early on that if you just guess all ones, you're going to get 0.5. So many people did that. So you'll see some certain plateaus that are what Kaggle identifies as these sort of benchmarks, where if you model based on trip length, then you'll get 0.58. So there's this, if Jason shows, yeah, that's 0.58. So you'll see kind of features like that where you sort of have a plateau, and then there's another one at 0.66 roughly. This is not a hard benchmark, but somebody had posted code in R how to use a logistic regression in order to get 0.66 on the leaderboard. So it's very easy to download this code and get 0.66 on the leaderboard. So there's these certain curves. But what this is going to show is sort of the evolution from mid-December until late March. And then eventually when we enter the scene, actually I think Jason had already made a contribution before the bootcamp even started. So we'll show up way before 3 months ago. But you'll see our rise as Jason's going to kind of narrate our approaches as we go on.
So the scores keep climbing, and now we
There's
enter the
VB
competition. And here we really got a poor scores, like we are exploring, playing, going in the eyes, explore DNA, didn't get any improvement.
Just get on the leaderboard, that's the idea there. And obviously more people can enter as the competition goes on, so there's kind of a shifting of the x-axis.
Yes, this is the first jump. Is like we realized we shouldn't use clustering and use the classification method.
Yes.
The GLM method, yes.
So that 0.66 is really an indicator for whether people use the internet or not.
Yeah, basically. That was why I kind of started doing this sort of analysis, is because you can see the hard benchmarks that they do. They'll identify, they're smart over at Kaggle, obviously. So if everybody's getting the same value, they'll say, oh, okay, we know doing it this way will get you this value. But it's interesting to see, especially this kind of soft plateau at 0.66, where maybe that indicates somebody on the forum found something and like everybody had the same idea. And so the idea was, okay, well, if you can see this visually on the leaderboard as time goes on, or if you're maybe casually browsing Kaggle and what the open competitions are, maybe you can get a daily look at the leaderboard. So this does some web scraping and gets the leaderboard for you that day. But you can see maybe there's something at 0.66 that I'm not getting because I'm at 0.55. So I'm going to browse the leaderboard 0.66 or browse the forums, maybe get an idea. But this is the logistic regression.
And also notice here is relatively steep, and this is a little bit hard, but like for us to climb up. Yes, and they basically out if we do trip matching can reach about 0.9 here. And from these days we start to use iterative process, kind of keep improve our result. And the last jump is from input. Oops. So here from clustering to classification. Then we keep improve our result, and at the end we add Alex's trick matching and keep improving our result. And at the end we see we ended here.
So we were kind of at the base of a very steep climb at the very end in the top 10%. So yeah. And just for fun, we plotted the #1 team, and they were always ahead. It was kind of disheartening, but.
Okay, we beat Edna and we reached the goal at the end. Learn something from the competition.
Okay. Thank you for your attention, everybody.
2 points I want to make. First, there was an objection to using such colorful graphs. So I just wanted to get that out there, but Alexander didn't like it. And secondly, I brought some homemade mead to celebrate finishing the Kaggle competition. It's 1 jug, but you guys are all welcome to come have either mead or beer when the mead runs out of the lobby. So hopefully we get to meet you guys. Yeah, thanks for coming.